Here we're looking at a figure from a paper on the topic of holographic data storage written by Dimitri Saltis and Jeffrey Burr. The paper appeared in a special issue of IEEE Computer Magazine a quarter century ago. The special issue was on the topic of optical computing. The idea here is that the holographic memory stores pages of information. So the spatial light modulator is encoded with a pattern of the data that you want to store, write it in the hologram. When you reconstruct it with the reference beam, you recover that page of data. How many bits can we store in that one page of that data? That's the topic we'll discuss today. Episode 11, Channel Capacity. Here we recall a slide from episode 10. The image at right calls to mind the fiber internet with capacity in gigabits per second. The image on the left is a CD-ROM with capacity of megabytes or gigabytes. Episode 10 focused on the accuracy with which the parameters could be estimated from image data using Fisher information. Today we want to talk about gigabytes, and we'll use Shannon information. We're going to talk about a measure of information. So suppose that we have some space x, and we know that we can measure n bits over that space. So then by this definition of resolution, we might say that our resolution is delta x is equal to the space size divided by n, which, as we've seen in the previous discussion, is going to be equal to 1 over twice the bandwidth. So that's a standard definition of resolution, and we want to understand how it arises. So we begin with the idea that we have a band-limited transformation. So here we have a transformation from f of x to g of x, our measurements, with only the constraint that we've convolved with the sinc function, which will naturally implement a band limit on the system. The imaging systems blur the object, and here the blur is associated with the sinc impulse response. We've also seen that measurements are made over a region with finite supports, so we're going to limit our measurements to the range minus x to plus x, as we've done previously, and we want to understand what is the capacity of this measurement system in terms of bits. So let's explore this. We're going to introduce, to do this, some eigenfunctions. It turns out that there are eigenfunctions of this transformation. Function psi sub n, such the integral of psi sub n against the sinc over a finite support yields an eigenvalue lambda times psi sub n. So we can find these eigenfunctions. One way to understand the nature of the eigenfunctions is to Fourier transform our band-limited eigenfunction, or our band-limited transformation. And if we do that, we get this form of the same equation, that the sinc turns into this exponential form. And we see that these eigenfunctions, psi sub n, have the form that they're also eigenfunctions of the Fourier transform over a region of finite support. So we get back phi sub n now evaluated at the spatial frequency with the normalization coefficients as shown. Now, it turns out that there are known eigenfunctions for this transformation. We won't get into the details here. The eigenfunctions were derived by a group at Bell Labs in the 1960s, Slepian, Polak, and Landau, and they used what's called Prolate spheroidal functions. So it turns out that Prolate spheroidal functions are functions derived in the coordinate system based on ellipsoidal analysis of three-dimensional space. So these are the transformations between the x, y, and z coordinates of three-dimensional space to their corresponding spheroidal term. So we can solve the three-dimensional wave equation in these coordinates, and it turns out that if we take the angular wave function in these coordinates, where the wave function will separate into radial and angular components, if we take the angular component, it solves the equation shown here. There's order numbers related to these indices m and n, and then there's this parameter c that will come up in just a second, and then eta here is the argument of the wave function. And so these Prolate spheroidal wave functions are solutions to this equation, and they were very, very difficult to calculate when this came out of Bell Labs in the 1960s. But today, they're not so hard to calculate. It turns out you can just plot them, and here we're using the Mathematica function, Prolate spheroidal PS. The PS here means that we're taking the spheroidal wave function Prolate and just doing the angular component. Here we've integrated the functions and developed a normalization that makes it so that they integrate to 1. So these are orthonormal functions. This parameter c is a value 10 here. And the interesting thing about that is that if you look at psi 0, it's mostly concentrated in the interval from -1 to 1. It turns out that the even Prolate spheroidal functions are even functions. So the psi 0 is plotted here only for positive x, but it looks the same for negative x. Now, that's the function that is band limited and is an eigenfunction of the band limited Fourier transform over finite support that is most concentrated in the interval between minus and 1, meaning that the integral of the function from -1, the magnitude squared of the function from -1 to 1 gives us the biggest eigenvalue because these functions are ordered in terms of the eigenvalue. If we go to psi 1, we would get the function that is orthogonal to psi 0, that is then an eigenfunction of the band limited Fourier transform and also concentrated as much as possible to get us a large interval. The odd functions turn out to be, the odd values of the index turn out to give us odd functions, so that this psi 1 would have a node in negative x that would go like this, and then that would make it so that it integrates to 0 when taken with an inner product with psi 0. Now here you notice as we go to larger and larger values of the index n, the functions get more and more of their structure outside of the interval from -1 to 1. So we get out here to psi 10. There's very little energy in the interval from -1 to 1, and most of the energy is outside that interval. Now this is because we've chosen this parameter to be 10 here. N is the Shannon number is equal to 10 in this case. If we chose a larger Shannon number, we would get to a larger index before the function went to 0 over the interval. So that tells us basically how many functions, and that tells us basically the kind of frequency the functions can oscillate at within the interval of -1 to 1 that will allow them to satisfy the constraint that they're orthogonal and band limited functions. Okay, so now this is a plot of the Prolate spheroidal functions themselves. It's also possible to plot them with Python. This is the SciPy library function to call the angular function of the Prolate spheroidal functions. Unfortunately, at the time of this recording, this function is not stably implemented, so we've used the Mathematica functions here to plot these functions. Now, if we integrate the function over the interval from -1 to 1, we get the eigenvalue of that corresponding function. So here's a plot of the eigenvalues for various values of the Shannon number n. So when n is equal to 5, the eigenvalue begins to fall right here at 5 and falls, to a very low value even by the time we get to beyond 10. That it's gone down by 5 orders of magnitude and going from 5 to 10. We make the Shannon number equal to 20. The number of functions, the number of eigenfunctions we get before the eigenvalue begins to fall goes out to about 20. We go to 40, it goes out to 40, go to 60, and so on. It turns out, so as we make the Shannon number larger and larger, then the number of functions that will have basically unity eigenvalues is equal to the Shannon number. Now, we can evaluate the projection of the object onto this Prolate spheroidal basis. G is just the band-limited version of the object. So if we integrate G against the Shannon number, we get the expansion of the we get the projection of f, the coefficient that represents f, on the basis of that, or projected onto that Shannon basis, because these functions are also band limited. So it doesn't matter if G is not if f is not band limited, we would get the band limited projection onto that Prolate spheroidal function. But we also have noise, and so we would also get the noise integrated against the Prolate spheroidal function. And let's say that interval gives us a value big N here for the nth coefficient. Now, we've divided by the eigenvalue lambda sub n, so that the integral of psi sub n against itself gives us lambda sub n. We've divided that out so that we just get g sub n is equal to the nth coefficient of f on the Prolate spheroidal, or the projection of f onto that Prolate spheroidal function, plus noise, but then now the noise is divided by lambda n. So up here where lambda n is equal to 1, that's no problem. We're going to basically, the noise hopefully is small compared to the signal, and so we would get a good estimate of f sub n for that value. But now down here where lambda n is below some threshold, this is a plot of lambda n here. So if lambda n is basically, when lambda n is 10 to the minus 5, that's going to be our signal to noise ratio is going to be 1 over that, would be 10 to the 5th, which presumably will be much larger than our signal. So we won't be able to recover that value. So basically this is why the number of independent values we can recover from the signal is approximately equal to the Shannon number, and this parameter of the Shannon number comes into the wave equation that we have for the Prolate spheroidal function and determines how many non-zero eigenvalues we have for a given system. And in general, if we have a system with a band limit, that we can show that the channel capacity is, and this would be the channel capacity per unit length, is going to be the bandwidth times the log of 1 plus the signal to noise ratio. So increasing the signal to noise ratio will increase the channel capacity, but only in the logarithm of the signal to noise ratio. This is the number of bits per second, the Shannon limit information of what we can send. Now, so what this is a limit on imaging systems ultimately, because we have a band limited system. So per unit area of the imaging system, the capacity will be equal to the band limit, times this logarithm of the SNR. We'll find later that the band limit is going to be approximately equal to 1 over the wavelength. So the capacity of an imaging system is ultimately going to be proportional to the area of the image divided by the wavelength squared, which brings us back to the discussion that we started today with, that if we have a page of data, how much information we put in that data, and ultimately it's going to be determined by the band limit or the point spread function of the imaging system. We'll find later that the point spread function will have a width that's approximately proportional to lambda times the f number of the system, and so the amount of information that we can store here is limited by that amount. Now, in the last lecture, in the last episode, I showed you that we can take an image and super resolve it with neural processing. That works very well for images that have some kind of sparse structure, but ultimately could not increase the channel capacity of a storage system. This Shannon limit is a very hard limit on the number of bits we can store in an image. Earlier in episode 5, we looked at wavelet transform. So here's an image, and here's the structure of an image on a wavelet transform. And we see the image itself is not sparse. It has information everywhere in the scene. But when we look at the wavelets, which are taking differences and finding features along edges, we find the image is very sparse. And so we would expect that we could find features in this image that we could improve the resolution of based on analysis of the distributed structure of the features. If we're going to store memory, though, we wouldn't store this kind of image in a memory. We'd store uncorrelated pixels. So we want in a memory system that each pixel in the image would be an independent value. So here's a random binary image. Now, what I showed you a second ago is if I take a normal image and take its wavelet transform, I find it sparse. If I take this random binary image and do the same thing, plot the wavelet the wavelet transformations of the averages and the differences, you find random patterns. There's no sparsity in any of the wavelet levels. And if we zoom into this, looking at some 10 by 10 region of pixels, you find that there's really no correlation between these images, which you would expect. The information should be completely independent. And so this Shannon limit is related to, if I have this kind of completely random data, how many bits can I store? How much information can I store in an image? You wouldn't be able to take the pattern of the averages, the differences here, and then try to estimate one of the other wavelet planes because it's just completely unrelated information. If we go back to the natural images, you find that there is this kind of structure. And so while the Shannon limit ultimately is a limit on what is the overall capacity of an imaging system, very, very few imaging systems find that as a relevant restriction because we just don't very often store random information in images. And as we'll see when we get into chapter 7, we are able to take natural images and estimate them with a much greater resolution, meaning now resolution in the sense that we talked about last time of how sharp spatially can we estimate a feature that limit is much finer than the Shannon limit might suggest. So here's an example that we'll talk about in Chapter 7 using this deep Laplacian pyramid networks to super resolve images. So we have the ground truth at the upper left, and we're looking at a variety of different estimation algorithms. The bicubic estimation is a linear interpolation of blurred data that's measured from this system. The ones that say CNN, those are using convolutional neural networks in their structure. And then we can get into more and more sophisticated structures. And this is still a very active area of extremely active research in terms of really analyzing the features and images and estimating with higher resolution. So this brings us to the end of Chapter 2, our study of forward models. What we're seeing in this slide is that the big problem we need to get to now is how do we take data from a forward model and estimate the scene, and that will be the topic of our next sequence of episodes. Computational imaging.